In this video, we're going to start our study of derivatives of vector-valued functions or derivatives of parametric curves. But to get to derivatives, we have to talk about changes. So we're going to look at how displacement is represented in vector-valued functions or parametric curves. We'll start with our classic example of motion around a unit circle, where the x-coordinate is defined by cos of t and the y-coordinate is sine of t, and that corresponds to a counterclockwise rotation around the origin. Now, just to pick two arbitrary times, imagine if we looked at time 0.5 and we looked at time 1.6 and said, what is the displacement between those two time points of the particle? And notice it's not about the trajectory that is covered over that time. It's strictly about the start point and end point. So when we look at this and measure the displacement is simply the end minus the start point. I'll just phrase it here as end minus start. With that idea in mind, we just sub in the value 1.6 into our function here. So we'll have cos of 1.6 and sine of 1.6 minus the cosine of the start point, which is 0.5. We'll highlight that here as a different color. And sine of 0.5, again in the same color for reference. And what we can see with that is if we calculate these values to a rough approximation, we end up with negative 0.03 and 0.99. And you can see that that corresponds nicely to the point just a bit past vertical for this cos of 1.6 and sine of 1.6, while the cos of 0.5, sine of 0.5 ends up at 0.88 and 0.48. And if we take a look at that, we're going to have one point minus another point that gives the vector connecting them, and that vector will be approximately this minus this, which is minus 0.91, and this minus this, which is 0.51. And we can see that we've got a left move of around 1 and an upwards motion in the y direction of 0.51. And so we get the components of that displacement vector. So a little more complicated than displacement in single variable functions, but certainly doable, subbing in the values and remembering that displacement vectors here would be endpoints minus start points. Now those are arbitrary values that we selected for that example. In general, we won't have a specific endpoint. What we do in calculus is ask, what if we start at a known location, but we allow ourselves some flexibility on the next point. So what we're going to do is we're going to advance in time about delta t, and then look at the position at 0.5, our start, plus delta t, and then figure out what the displacement vector is joining those 2 points. What that's going to give us is a function. The displacement, this vector here, is going to depend on the value of delta t. The nice thing about this is that the displacement is going to be formatted exactly the same way it was last time. We won't get into the weeds of the values here because we won't know what delta t is, but we just remember that the formulation of it is exactly the same. It is the end minus the start. Then we could also go one step further here and actually express it as individual values in sine and cos for the x and y coordinates. It's a little less beneficial here simply because we can't tidy any of these values up, but it's still true. So we'd have the endpoint minus the start point, which is that same function evaluated simply at 0.5. And there we are. So that is displacement starting at the point time 0.5 and moving to some time later, presumably a smaller time later, but it doesn't have to be. It could have been a large time step. This formula would apply in any of those cases. So here's our first question. If we imagine this displacement and we look at the vector that we get from it, ask yourself what will happen as delta t gets smaller. That's going to be one of the anchoring points of any calculus question. What happens as we look at smaller and smaller time intervals, or in space, smaller and smaller space intervals? In also calculus speak, we would consider that to be a limit question. What happens in the limit as delta t goes to 0? Then simply ask yourself what happens to that displacement vector. Take a moment to read over those two options, and then we'll investigate. All right. Well, if we imagine small time intervals, what we get is less motion, right? Because we have less time, and that leads directly to less displacement. In fact, if we ended up with delta t going to 0, there's actually no problem with that. As delta t goes to 0, the start point and end point are identical. And that would be 0 displacement. So we're definitely going to have the displacement vector shrinking as delta t gets smaller. And that's fair enough. If you ask yourself, how far do I move? Say I'm moving around a circle. How far do I move in 1 second versus 0.1 seconds versus 0.000001 seconds? Well, we're going to move less and less as the time interval gets smaller. What's interesting is when we do a proportion, though. Let's investigate that side of things.